Extending the Galileo experiment model just a little further, depth versus clock time was given by this function. Velocity versus clock time was given in three different ways. First, by an estimated best fit on the average rate of change versus midpoint clock time. Average rate of change versus T-mid. And both of these are from the average rate of change versus T-mid. This was from a hand graph, so the 0.10t plus 0.5 from a hand graph was this. Excel best fit was this, very close. The only difference between the 0.5 and the 0.49. We would not ordinarily be that close with a crudely sketched hand graph. That was a kind of a stroke of luck there. We don't expect to be that close, so don't count on that sort of thing. But if we do a good graph, it can be pretty good. And then the derivative of the best fit position function, which was this function obtained by the best fit from the original data. And we see that these three all have the same slope, all have the same coefficient of t, and vary just a little bit in the value of the constant. So that would indicate that we have a great model. Or does it? Well, if I take this information over here to see what our best fit model, our best fit quadratic model, write this small so nobody can read it. Okay, our best fit quadratic model, and I probably have that up where you can't see it even if you wanted to read it. Okay, implies what? Well, a graph of this function would have a vertex t equals negative b over 2a, very easily found to be negative 4.5, and the y-coordinate of the vertex would be 26, just plugging the negative 4.5 in for t and evaluating it. So the vertex t would be this, so the vertex is at negative 4.5, 26. Now, what do we know? And also, using the derivative of this function, the velocity would be the 0.10t plus 0.45. So this still follows from the best fit quadratic function. V of 1, which we know to have been 0, that's where I released the ball at count 1, was 0.10 times 1 plus 4.5, or 0.55. Now, it's possible that I anticipated the count, started counting later than the time at which I released the ball, but I think I can move my finger and say 1 at very nearly the same time. I don't think that was a problem. You might think of what other factors could have caused this discrepancy, but that's a fairly significant discrepancy. We have 4 counts. Before I started, where the quadratic model indicates that we would have actually started, and that we would have actually started at 26. So 4.5 counts earlier, and 3 centimeters prior to the left of our initial position. So that's not a huge serious discrepancy, depending on what you're wanting to conclude from the data, but it's not trivial either. And we also know that V of 1 is 0, not 0.55. Well, I mentioned that just a minute ago. And if really quadratic, the vertex would be at t equals 1, y equals 29, not at negative 4.5, 26. So we draw the conclusion that the model does have some flaws. So we got to be careful. We have to be careful. We have to check internal consistency within a model. We have to check the model against reality. And we have to take the model with a grain of salt. Now, I'm going to pause the video and put up the graph that we originally had. to show you how, again, the vertex and the displacement of the vertex and the assumptions about initial velocity aren't all that consistent with our data. If we look at our original graph of position versus time, we assumed that in creating this model, that the initial velocity was 0, which means the slope of our position versus time graph would be 0, but that's not really consistent with the trend of this graph. This graph still has a positive slope when we get down to t equals 0. And that would be consistent with the graph dipping down a little further, so that by the time we get to negative 4.5, maybe about here, we are finally at the vertex of the best fit model. But that the best fit model doesn't correctly mimic the initial velocity, the initial condition that the velocity is 0 when t equals 0.